Are we ready for a 3x3 system of linear equations? Here's our steps. We're going to target one of the three variables for elimination. We're going to eliminate the targeted variable from one pair of equations, eliminate the targeted variable from a different pair of equations, solve the remaining 2x2 system for both variables using either substitution or elimination again, and then back substitute known variables into one of the original equations to find the value of the targeted variable. Ooh, sounds like fun, doesn't it? All right, I'm going to go ahead and delete out my work from previous years, and let's do this. Solve the system if possible. Classify the system as consistent and dependent, there's a typo there, dependent, or inconsistent. I didn't see that earlier. Okay, so we need to target one variable that we want to get rid of. There's different ways to do this. So I like to usually look for something that's going to be pretty easy to multiply two different equations by two different things and add them to a third equation that we do nothing to and get rid of one variable. So you'll notice right here we have two negative y's and a positive 4y. So if we multiply this equation by 4 and this equation by 4, and then we add these two together, and then we add these two together, we will eliminate the variable y. We could also multiply these two equations by a negative 3 to eliminate the variable z. Or the last possibility would be to multiply the bottom equation by a negative 3, add it to the top equation to get rid of x, and then go back to our original problem, multiply the bottom equation by a negative 2, add it to this equation to get rid of x. So it really doesn't matter whether we get rid of x, y, or z, we just need to choose something and go for it. Now in some problems it's more obviously simple to do one variable over another one. In this case I don't think any of them are any more easy than any others. If I go ahead and get rid of z, then I'll be used to just having my x's and y's for the last part of the problem. But that's not necessarily an advantage to get you used to that. Why not just have x and z, or just y and z, correct? I'm going to make my decision to get rid of y. That's my final answer. Okay, so I'm going to take these two equations, and I'm going to multiply this top one by a 4. So 4 times 3 is 12. And 4 times negative y is negative 4y. 4 times z is 4z, and 4 times 3 is 12. I multiply everything by that chosen number. Then I'm going to multiply the next part of that with, nothing. I don't need to multiply anything for that bottom part. We're just going to copy that over. So 2x plus 4y plus 3z equals 16. Add those together, we get 14x, we get 0y, I'm not even going to bother writing it, plus 7z equals, make sure I'm adding correctly, I believe it's 28. Okay, we're going to set that equation aside for now, because that's one of our new 2x2 equations that we're going to use to solve x and z, and then we'll come back to these three equations and find y. Okay, let's go ahead and do y again, because now that we chose y in the first place, we're going to choose y again, or else our plan is not going to work. So we've got to multiply this by a 4. So that gives us 4x minus 4y plus 4z equals 5. And then we're going to take that original middle equation again, 2x plus 4y plus 3z equals 16. So you're always going to use one of the equations twice in this process, and then each of the other equations once. Okay, let's add these together. So that gives us 6x plus 0y plus 7z equals 21. We now have a system of two equations with two unknowns, and we just saw exactly how to do problems like that, right? So just to summarize, I have 14x plus 7z equals 28. and I have 6x plus 7z equals 21. I'm going to forget about y for a minute and just say this is my system. Okay, so forgetting about y, let's approach this like we just did our 2x2s. How are we going to get rid of one variable? Well, I think the most obvious thing to get rid of here would be z. And the easiest way to do that would be to take one of our equations and multiply through by a -1. So that would change this bottom equation to negative 6x minus 7, oops, I keep writing 7 as a z. So minus 6x minus 7z, better, equals negative 21. And then I'm going to add that new equation that I just made by multiplying by a -1. I'm going to add that to the other equation. So I'm going to add those two together, right? So let's do that, and we get 14x minus 6x is 8x, 7z minus 7z is 0, and then 28 minus 21 is, dun, 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 did I do something wrong? No, I think it's right. Does this have really ugly answers? Do you remember from before I erased everything? I'm suddenly worried that I added something wrong somewhere. And I suddenly want to go back through and look so I can tell if I've done something wrong. So hold on a while. Welcome back. Upon inspection, I discovered that I did not multiply everything through like I was supposed to. So right here, you might have seen my mistake earlier and been like, oh no, she did it wrong, the whole thing's going to be messed up. At least I figured that out before I got too far when I realized my answer was going to be a fraction. And that was not necessarily making me very happy. So change, multiply everything by 4. That turns our 4 times 5 into a 20. That means we add our 20 and our 16 together, and we get 36 there, which means that this 21 is actually a 36. And this negative 21 is going to be a negative 36. So 36 and negative 36, and we're adding our 28 and our negative 36 together, which gives us a much better answer of negative 8. So then we divide both sides by 8, and we get x equals negative 1. Whew! I mean, you can get fraction answers, but it is just not going to be a happy ending if we were to have a fraction at this point in the game. Okay, now going back to what we just learned about 2x2 equations. Now that we have one of our x values, we can find that, plug that in, and find our z value, right? Doesn't matter where we plug it in exactly. So we could use these numbers or these numbers, it doesn't matter. But we're not going back to the original, we're going back to the step we did right before this, where we got our 2x2s. We plug that into there. So 14 times negative 1 plus 7z equals 28. So that's negative 14. So I'm going to add 14 to both sides. So that gives me 7z equals whatever 14 plus 28 is. I believe that's going to be 42. And then 7 goes into 42 6 times. So z is 6. All right, now that we know x and z, we are going to go back to one of our original problems. Let me pick a whole different color here to do this. So we know x equals 1, negative 1 rather. We know z equals 6, and now we just need to find y. So go back to one of these original problems. It doesn't matter which one. Pick one. I'm going to go with the bottom one. So I'm going to go with x minus y plus z equals 5. I chose the bottom one because the numbers are really small. So I plug in the 6 for z, and I plug in the negative 1 for x. So negative 1 plus 6 is 5. So then I would subtract 5 from both sides, and I get negative y equals 0, which means y equals 0. So that y value is simply 0, and there is our solution set. I almost forgot to classify it. So this has one set of solutions, which means this one is consistent. I have know why I'm marking that typo again, but this one is going to be consistent independence. There's a solution, and it's only one solution, one set of solutions.